Saxon Algebra 2. This is Jayla's final recap. There are just 2 lessons, Jayla, that I want to give just a little additional review on, and then I'll have you retake 2 of the questions from yesterday. Not because you need it for your grade is fantastic. Not because you need to do it for me. I'm completely confident that you've mastered this material well within the range of what's acceptable, in terms of grades. You're way up there. There's not a concern that I have about that. I am a huge admirer of your very careful, deliberate, precise way of working problems. I just want you to end this class and top off all of your hard work with a huge success here at the end. And there were 2 problems that just got the better of you, and I don't want them to win. I want you to win. So that is why we're just doing a little review, and then I want you to look at those problems again. The first area, it was question 3 on the final. And the topic was from lesson 115, exponential equations. So I'm going to ask you to just follow along as I recap this. If you still feel at all, I don't want to say confused, but if your Jenga tower isn't strong and solid, go back and watch the video for lesson 115 one more time, if you would be so kind. But in the meantime, I'm going to do a different problem than the examples in lesson 115. The problem that I'm going to do is from the problem set for lesson 117. It's problem 2, so you probably haven't done it yet. Oh wait, that's not right. It's 12. My bad. 12, okay. It's about rabbits. It's about the number of rabbits increasing exponentially. At first there were 85 rabbits. 12 years later there were 1,700 rabbits. How many rabbits would there be at the end of 130 years? Oh my gosh, there's so many rabbits in my neighborhood. I guess in all of Seattle, they've just been sort of exploding lately. So this is stolen from today's headlines. Okay, so what is the formula we use? That was a source of a little bit of wobble for you on the test. This is the formula you want to use for the scientific version of the problem. You were confusing, I believe you had parts of this is the business version, and this is the science version. You were taking elements of both and confusing them, and that was part of the problem. This is the one that we want to use for our rabbits, okay? And honestly, I don't worry that much about this one, because this one, if you just understand how the variables translate, this one can be used for everything. So I kind of get annoyed by that. All right, remember these are 2-step problems. So the first step is to use some of the data to solve for k. Remember, k is a component of the exponent on the natural log of e that is valid for the problem. So we have to use the information that we have on the first scenario to solve for k. And for the first scenario, it says at first there were 85 rabbits. Okay, so we know that's the original amount. 12 years later, so when t equals 12, the amount at 12 years is 1,700. Right? Okay, then it goes on to talk about the second scenario. So we can stop right here, and we use this formula to solve for k. So I've taken this information and substituted it into this equation. The amount at the end of the time that we're talking about, which is 12, is 1,700. That equals the original amount times e to the, oh, I did this wrong. I substituted 12 in for t, right? And I put that first, and then k is what we don't know, and I just flipped the order of those because I like to have my number before my letter, right? So we know t, we don't know k. We know the original amount, and we know the amount after 12 years. You set this up wrong. You had things on the wrong side of the equation. You were really confused at this point. So again, look at how I took this equation and substituted in this information. Now I need to solve that. Okay, so number one, fill in the information. Number two, solve. The first thing that we can always do to solve is divide by the number here that's in front of the e with the exponent. That's always going to work out beautifully. So now this goes, and let's see, I can guess 85 goes into 170 twice, right? 16, 17, yeah. So that number is 20. So now I can say 20 equals e to the 12k. Now, so this was easy, right? This had nothing to do with the exponent. That's just dividing away the number that's sitting in front of the e. There's no exponential hoo-ha in that. Second, I realized that I don't have my calculator because it's busy being part of my phone that's recording this, so I'm going to have to rely on John for some help here. Okay, so what we need to do now is use the calculator to find the exponent that goes on e, our natural log, in order to reflect the number 20. And according to John, that is the number 3.00. The way you would find that is you would enter 20. Obviously it's a 2 and a 0, but you know what I mean. And then you'd hit the natural log button. And then that would give you, according to John, 3.00. I wish I would have checked that before I started this video because there's nothing I can do now. But that tells us we can rewrite this as e to the 3.00 equals e to the 12k. All right, so we've rewritten 20 as an exponent on the natural log. All right, now we can take the exponents and make them equal to each other. 3 equals 12k, divide both sides by 12, and we get k equals 1/4, or because it's science, we like to do 0.25. All right, so I'm going to flip over. I know that k equals 0.25, and I'm going to rewrite my formula. You just have to hardcore memorize this. EKT. Okay, and now we're doing, so we did our first step, that's to solve for k, and now our second step is to deal with the other one. How many rabbits would there be at the end of 130 years? So now our t is equal to 130. We still need our original amount, which was 85. Right? Okay, so the amount at the end of 130 years, which we don't know what that is, equals the original amount, 85, times e to the k times t. Now we can figure that out. Our new time is 100 and, well, let's do the k first. 0.25 times the time, which is now 130. Make sense? Okay, so let me just double check. This is all looking good. Yep. Okay, and so now we run this into the calculator, and this is how you do it. Start with 130. Multiply that times 0.25. Then do an equals. Then do e to the x, because this is the exponent that we want to put on e. And I think you need to do an equals again. Then times, look at my row of weird buttons, 85. Obviously, those are two separate buttons, but you know how to do that. All right, so we're working from right to left, which feels backwards. First, we multiply these two. Then we use this button to calculate the power of e. And then we multiply that answer times 85. And the answer that you will get is a big number. It's just a decimal. That dot up there doesn't count. 1.11 times 10 to the 16th rabbits. This may kind of freak out your calculator. This, if you can get to this point, you'll get most of the credit on the problem. Running it through the calculator is worth like half a point to me. All right, so a two-step problem. First we solved for k, then we used k this way. I think well, I shouldn't guess, but I think the fact that you weren't really certain on this formula was what took you down at the knees. So memorize that and make sure you're clear on the two steps of how to do that. Okay, that was problem 3 on the final that messed you up. The other problem that I want to talk about was the permutation problem, which was actually it was review problem for April 27. This comes from lesson 116, okay? Here's the thing about permutation problems. That is both their charm and their frustration. No two are ever exactly alike. And there isn't a straightforward formula that we always use to plug in variables and make it work. We have to logic through each scenario and try to make sense of it. We have to do them independently. We have to kind of work on them independently from one another. Okay, so I'm going to try another one. This is from problem set 117 again. This is problem 6, okay? And this is not exactly like the one on the test, but it gives you an idea of how to think through them. Roosevelt has 5 different flags and 8 flagpoles in a row. How many different ways can she fly her flags if she flies all 5 flags every time? So, what we do, this one's a little confusing because I wasn't sure if we should focus on flagpoles or flags. But we're going to look at the flags. So here are her 5 different flags. Now, a flag is a physical thing. She doesn't have endless numbers of each kind of flag. She only has 5 of each, or 1 of each flag. There's 5 in all. So that limits how she can arrange them. When she goes to hang up her first flag, she has how many flagpoles to choose from? She has 8. When she goes to hang up the next flag, she only has 7 flagpoles, and then 6, and then 5, and then 4. These are concrete things. She has a limited number of flags and a limited number of flagpoles. So John doesn't have to tell us without replacement, because we know flags are not just infinitely replaceable. That's not the way it works. So that's how we know to have them descending in number. And there's the final answer. This is hardly the important part. The important part is laying out the numbers and understanding the patterns. Let me talk about the one that we talked about on the phone for a long time. It was a 6-digit license plate. There are the 6 different elements. And we were told that the first 3 are letters and the last 3 are numbers. Okay? So, how many different combinations are there? Well, letters means we're drawing from the alphabet, right? There are 26 letters in the alphabet. We can use the same letter over and over again on a license plate, right? There's no physical limit like there were flags in this problem. This one, it doesn't have to tell us, well, I think he does even tell us. I don't have that problem in front of me, but you remember it. So there are 26 letters she can choose from here. 26 here and 26 here. Maybe I'm making it different. Maybe the problem said you couldn't repeat the letters. But in my problem, I'm saying you can repeat the letters. With the numbers, we have how many digits? We have 0 through 9. That is 10 digits. That was a place where I think your brain was hiccuping a little bit. Maybe it was just because it was late. But just because the digits go up to 9 doesn't mean there's 9. There are 10 digits in our system. So there are 10 digits here. So you had to think, okay, letters, how many choices do I have? Number, how many choices do I have? This is with replacement. This is my version of the problem saying, yeah, your license plate can start with DDD if you want. It can be 3 letters in a row. Let's say that you couldn't have replacement. Still 6 places to fill in. First 3 are letters, first 3 are numbers. So this is without replacement. Okay, so we have 26 letters of the alphabet still. You plug it in. Now, the next time you can't repeat it, and the next time you can't repeat those either. Now we're done with the letters. That's all for letters. Now we switch over to our numbers and our digits. How many digits do we have to choose from in the first blank? 10. 0 through 9 represents 10 digits. If we can't replace them, then that means we go to 9 and to 8. Okay? I don't have the numbers for running those out. I don't have my calculator available to me, as you well know. But this is the challenge of permutations, is that you have to logically think about each scenario. You have to either notice what John says about whether or not there's replacement, or you just have to use common sense, right? Flags can't be replaced. Once you've hung it on one flagpole, you can't hang it on, well, I guess you can technically hang 2 flags on the same flagpole, but that's kind of overthinking the problem. So you have to do your best to think about each scenario, think about what kind of element you're using to fill in the blanks, and think about how many are left. I just want to look at your test for a second. Oh, what was the review problem? My bad. I'm just flipping through your papers to see if there's anything else I can give you. Yeah, pay attention to what the problem tells you about replacement, or another way of saying that is repetition. If an item can be repeated, then that's the same as replacing, okay? And honestly, that was your mistake in this one. It says right in the problem, remember that digits can be repeated, but you did it the other way, okay? So remember that if you can repeat the digits, then you have the same number to draw from each time. It's only when you can't replace that you need to count down. So my advice is try a few more of these problems. They are from lesson 116, so that's what you look for in the parentheses. Check your answer carefully and make sure you understand the solutions manual version of the answer so that you know what you're doing. If you have other problems that are bothering you, like if you can't get them, send the number to me, the lesson and the problem number, and let me help you figure that out. Okay, those were your only 2 problem areas, Jayla. Go ahead and study those, and I'll be in touch with you to talk about rescheduling.